Alright, okay, here we go. So here's another problem we all know and love. Good old vertical loops and centripetal force problem. Alright, so this is the last one on our last test. Alright, centripetal force test. Alright, so I'll read it to you. A ball of mass M, capital M, attached to a string of length capital L, moves in a circle in a vertical plane as shown above. Alright, that's this diagram right here. It's actually shown below. Alright, at the top of the circular path, the tension in the string is twice the weight of the ball. At the bottom, the ball just clears the ground. Air resistance is negligible. And then they say, express all of your answers in terms of M, L, and G. So this confuses a couple, some people get confused about this part. How am I supposed to answer this all in terms of these variables? It gets annoying, but once you get used to it, it's really not all that different, and sometimes these problems are even easier. Because really you don't even need a calculator to solve it. As long as you understand basic math operations, addition, subtraction, and squaring and square roots. I mean, the entire thing is basic algebra. It's not that difficult. It's just the difficult part. It's a matter of figuring out what variables you have and where they're going to plug in. All right. So it looks kind of weird without numbers, but it's still basic math operations, right? How many different ways can I say that it's basic math? We'll find out. Alright, so here we go. Determine the speed at the top of the loop. Right? Well, before we can even answer that part, we'll just take a step back. Let's look at the original information given to us in the problem. At the top of the circular path, the tension in the string is twice the weight of the ball. Alright. So if they haven't given us an actual mass, they haven't given us a velocity, right? Or they haven't given us a period or anything, we're going to have to do some detective work, right? We have to read in between the lines in order to figure out how we're going to set up these equations, right? Because the normal information we're used to getting it's not here this time, right? So then why are they telling us this? At the top of the circular path, the tension in the string is twice the weight of the ball. Right? Well, this diagram isn't for that specific moment. Right? If we were at the top of the circle, right, if the ball was right here, going towards the center of the circle, that's the positive direction, right? Center of the circle is always positive, whether you're at the top of the circle or at the bottom. And when they say the tension in the string is twice the weight of the ball, they're really giving us a ratio between the only two forces that are involved, right? Obviously, centripetal force is involved, but that's a measure of our net force, right? The total force is causing this circular motion. But when it's at the top, right, gravity obviously goes downwards. Gravity has to go down, right? But in this case, down is the positive direction. So that's new, that's different, right? But that only happens during circular problems. And then tension is downwards also, right? But they're both in the positive direction in relation to the circle. All right, so they gave us enough information to figure out our net force equation. Even though we don't really know what the values of these are, we do know how they all line up together. We know how they're combined. Alright, so then let's go back. The tension in the string is twice the weight of the ball. Alright, weight's just a fancy word for force of gravity, or actually force of gravity is a fancy word for weight. But you should know that by now. If you don't know that, well, just go study, okay? Fg stays the same, right? And they're telling us that Ft is equal to 2Fg. So really, all in all, at the top of the circle, at the top of the loop, the centripetal force, it's caused by tension and gravity, but the total magnitude is just equal to 3 times the force of gravity. Right? So we know that Fc has to be equal to 3 times mg. Alright? Well, how does that help us? How does that help us with part A? How do we know determine the speed of the ball at the top? Right? Well, our original equation for tangential speed, 2 pi r over t, right? We know the radius. but we don't know the period. We don't know how long it takes to do this, so we have to find an alternative way to solve for VT. And coincidentally, right, FC is equal to mdt squared over r. We have VT, it's in another equation, it's in your centripetal force equation, right? It's also in centripetal acceleration, but look at that. We have centripetal force is equal mvt squared over r, but we also have the magnitude, right? This is just the equation, but this is the actual magnitude of that force. It's 3mg. Right, so if we were to set these equal to each other, right, if we were to substitute, we find out that you have the same mass on both sides. Right, it's referring to the mass of the ball. But you know what? They want us to use these special variables. They want us to use capital M, capital L, and lowercase g. Alright, so then let's do that. Let's just replace them all real quick. Right, you're really just making the m's capital, and then your radius is just capital L. Right? Nothing different in the equation, nothing different in the math. We're just plugging in these weird letters instead of numbers, right? But the way that they're all related, the way they all come together, it's still the same. They all behave the same way, right? So we got a mass over here, those cancel out. So you're left with 3g is equal to vt squared over L, right? So then multiply both sides by L. Bring your L over, 3lg is equal to vt squared, right? So that means we're solving for vt, right? That was part A. Right? Let's put my camera down a little bit. Just take the square root. So the answer to this, part A, right? Determine the speed of the ball at the top of the loop. We don't have a numerical answer. If we did have numbers for the length of the string, then we could plug those in easily, right, and get a numerical answer. But they didn't give those to us, right? Really, this is like a general application. It's almost kind of like we found a shortcut equation. If you ever did run into this problem again, if you ever saw it again and they gave you an actual radius and a mass, right? Well, all you need is the radius for this one. If they gave you a number, you can just plug that in very quickly and get your numerical answer, right? Unfortunately, that's not the case. The people who make the AP exam, they like to confuse high school students. So you do see these pretty often, right? The fact that you're using letters instead of numbers is just testing how well you understand the equations, right? Do you understand how they form together, what variables are in the problem, and where are they going to go inside those equations, right? So part B, I know this keeps coming out of focus, all right, but part B, let's zoom in. Determine the time it takes the ball to reach the ground if the string is cut when the ball is at the highest point of the circle. All right. Well, that's interesting. When it's at the highest point of the circle, right, it doesn't matter, it doesn't even tell you if it's going clockwise or counterclockwise, right? But it's basically just going around and around and around. And if you release at the very topmost point, it shouldn't have any vertical velocity at all, right? Technically, it would be going tangent, right? It would be going exactly horizontal to the circle, right? Or it would be going horizontal, in the horizontal direction, aka tangent to the circle, right? So that's the direction it wants to go. So this, it seems like a complicated circle problem, but really it's half of a projectile problem, right? When we let go from that point, it would begin to go tangent at first, but then it follows that parabolic curve, right, that all projectiles follow. So if it starts off, if it's just going horizontally, if there's no vertical velocity at the beginning, right, or at least at the beginning of part B, then all you need to solve for the time is the height, right? All objects are going to follow at the same acceleration rate due to gravity. So as long as you know the height, doesn't matter what your horizontal velocity is, as long as you know the height that it starts from, you can figure out how long it takes to hit the ground, right? So this is an old equation, right? Remember good old d is equal to di plus pit, right? And these are all y variables. 1 half AYT squared, right? We're solving for the time that it takes to hit the ground. It's only dependent on the height and your y velocity and your y acceleration. Any horizontal variables have nothing to do with this. Alright, so we have this nice neat equation here. It's ready to go. Alright, but what's our height? Well, if you remember back up here, right, they gave us some weird looking info. At the bottom the ball just clears the ground. Why would they even add that? Why is that important? Why are they telling you this? Well, they're saying, right, the radius just reaches the ground, right? So the radius is really, it gives you an idea of what the height of the circle is going to be, right? If the radius is just L, then the entire height, right, from here to here, that should be 2L. So when it gets launched horizontally, right, not vertically, when it gets launched horizontally, our original starting position is 2L. Right, so technically this is the displacement right here. All these D's in this equation is displacement. But because we're starting from the top, it's falling the entire time, you're allowed to use positive variables, right? That's the one case when you're allowed to make gravity positive, right? If it's just falling, if it starts from rest, if it's falling and it doesn't change direction, right? If this were a different problem, if it was thrown up into the air, then you need to take the negatives into account. But these ones, you're allowed to use the shortcut. You can leave everything positive, right? And our initial y velocity is 0, so everything over here is 0, right? And this just becomes 1 half. Our acceleration in the y direction, they just want us to leave it as g. Alright, so this would be 1 half gt squared. Alright, so that's everything that we can plug into the equation. So it looks messy, but it's just basic algebra. That's all there is to it. Alright, so we got 2L over here is equal to 1 half gt squared. Alright, I'll do it one step at a time. We have 1 half in front, so if we multiply both sides by 2, that would get rid of that. So we have 4L is equal to gt squared. If I get rid of that, so we have 4L over g is equal to t squared. Right? So then we just take the square root. T is equal to the square root of 4L over g. Right? But don't forget, you can simplify within the root. Right? 4 is the square right there. So this just becomes 2 times the square root of L over g. And once again, I read an annoying answer, but that is correct. That is the representation of how long it would take in terms of these variables and these variables only. Right, so we have L and G. And then, so that's how long it would take to reach the ground. And then our last part, right, determine the horizontal distance traveled by the ball if the string is cut when the ball is at the highest point of the circle. This is exactly the same thing as when we did those half projectile problems, right? It's thrown horizontally from initial height. How far away does it land from the base of the cliff? Remember those? Except now we're not dealing with the cliff, it's just a circle, right? All you gotta do, we have the time that spends in the air, right? And the horizontal velocity it's launched with. Right, so I'm just gonna draw it going this way this time, right? So if it starts from up here, it's gonna follow a parabola. Right, and it's going to land a distance away, and that's dx. Right? Once it's launched, there's no forces acting on it horizontally, so our horizontal velocity is constant. There's no acceleration in the x direction. Right? So in order to get the distance, it's very, very easy equation. Right? dx is equal to vx times t. You are only allowed to use this equation when you have constant velocity. Be careful, because I still see kids who are trying to use this equation for problems that involve acceleration. Right? Well, technically there is acceleration involved here, but it's in the y direction. Right? These are only our x variables. But if you have constant velocity, you have to use the constant velocity equation. Right? So final distance in the x direction, how far away does it land? It's just these two answers multiplied together. Right? This is our vt at the top. But that becomes our horizontal velocity that we're launched with, and that's the time that it takes to hit the ground. Alright, so this is root 3LG times 2 root L over G. Right, kind of running out of room there. But these are multiplied, and you are allowed to multiply, right, what's inside the radical. Right, so 3LG will be multiplied by L over G. Alright, so let's do this. I'm probably running out of room here. Let's see. There. Seamless transition. Alright, so then this would be dx is equal to, alright, so let's the 2 goes out in front, and then we'll multiply the radicals together, right? L times L, well, the 3 goes first, right? But then L times L, you get L squared. And then G over G, wasn't that interesting? Those cancel, those are going to end up canceling out, right? Our G's cancel out, and then you have an L squared inside the radical. So that becomes L. So all that you're left with, right, dx is 2L, and then the only thing left inside is the 3. Right. And there you go. There's your answer right there. There's your final answer. It looks messy, but that is indeed the correct answer. It is a measure of how far the ball will travel horizontally, only using these variables at the top. I just dropped my answer there. Right. M, L, and G. Those are the only variables that are in our answers. Right. And then there's your final answer at that. Alright, cool. See you next time, kids.